In worksheet 3, we're going to work through a number of mostly empirical probabilities where we define an experiment which gives rise to the sample space of outcomes of the experiment, and then by counting and taking ratios or relative frequencies, we can calculate probabilities in this form. The other notion that we've studied briefly is the theoretical probability based on random variables and the outcomes from experiments that arise when we define either a discrete or a continuous random variable. So the empirical results that I'll show you here are just based on ratios of the number of elements that correspond to the event A, for example, compared to the total number of elements in the sample space. In this case, our sample space is countries. If we add up the number of countries given in this problem, we'll have a denominator of 194. Okay? I won't go through all of these calculations. Most of you did this correctly, but I just wanted to set the stage for how we would use relative frequency, which is a term that we've already introduced several times in the preceding worksheets. Okay. Exercise 2 is another experiment using a deck of cards, and these are fairly innocent looking problems. Some of you have played poker and other card games, and some of you have played roulette and dice games, and you know that it's, of course, figuring out, for example, in poker how to calculate the probability of a royal flush. When you go to the video machine, you'll see a huge jackpot for a royal flush, and you'll sit down and, who knows, maybe spend hours trying to win that jackpot. Well, the reason it's so elusive is because the probability is so small. Okay. Anyway, I'll skip this problem. Again, most of you did this correctly. Where I had some question was, did you justify your solution, or did you just simply write down a solution here? If I just saw a number, for example, if you wrote solution probability of A is 1/2, and that was it, I couldn't give you full credit. Okay, so be sure that you qualify or justify each of your answers with a mathematical argument, using formulas, using definitions, instead of just writing down an answer. That won't get full credit. Okay, let's move into 3 now. Number 3 is a little bit more complicated, where we have joint events, that is, events that happen serially. They may happen at the same time, and we need to be able to parse out the words in the problem. And if we want to compute relative frequencies or probabilities, we need to be able to count the number of outcomes in S, the sample space, and then the number of elements in the event that's been defined. Okay? And we also want to know about relationships between events. Can they be independent? Can they be mutually exclusive? And so on. So let's go through this problem now. It's got some interesting ideas in it. So the deck here that we're dealing with has 10 cards, of which 4 are green, 3 are blue, and 3 are red. When a card is picked, its color is recorded, and then we toss a coin, and then we assume that it's a fair coin. That is, the heads and tails are equally likely. So let's go ahead and list the sample space. And if we do that, we can write the sample space depicting the joint events of drawing a card from the deck and then tossing a coin, a fair coin. We can depict the sample space S as having these 6 outcomes. Why 6? Well, because we have 3 colors in our deck and we have 2 outcomes from the coin toss. So we have a total of 3 times 2, or 6 outcomes. Color, green, blue, or red on the first draw, and then a heads or a tails on the toss, which comes after. Okay. All right, let's define A as the event that the blue card is picked, followed by a head on the coin toss. All right. So we know that these 2 events are independent. The draw of the card is independent of the toss of the coin. So the probability of the joint event, that you have a blue card followed by a head, is simply the product of their probabilities. Since there are 3 blue cards in this deck of 10 cards, we know the probability of a blue card is 3 over 10, and then multiply by the probability of the head, which is 1/2, and we get the 3/20ths. Okay, now let's look at event B here, where B is the event that a red or a green is picked, followed by landing a head on the green on the coin toss. Well, A is drawing a blue card. So these are mutually exclusive events, aren't they? Irrespective of what the coin toss is, because you're never going to have an outcome falling in the set A and the set B, because the colors are different. So obviously you cannot pick a card that is both blue and then red or green. Okay, so therefore the 2 events are mutually exclusive, and we get a 0 for the probability of A and B. Okay. Now we'll assume that C is red or blue. All right, C admits that a blue card can be picked, and that's precisely what A is doing. It's picking a blue card, so these are not mutually exclusive, and you can see that probability of a blue card followed by a coin toss and a red or green card followed by a coin toss is simply the probability of A, okay, which would be 3 over 20. All right. Okay, so there we have number 3. In number 4, we are given the following scenario. We have 2 events, C and D, and we're given the probabilities of C, D, and the probability of C given D. The conditional probability of C given that D has occurred. Okay. So first of all, let's find their joint probability of C and D, and to do that we'll use our formula for the definition of conditional probability. And there are 2 ways to write this formula. Let's write it in terms of the probability of C and D, and that's equal to the probability of D times the probability of C given D. Both of those probabilities are given in the scenario up here. The probability of D is 1/2. The conditional probability of C given D is given to us to be 0.6. So when we multiply these 2 numbers together, we get 0.3. Okay. Part B, are C and D mutually exclusive? Why or why not? Okay. Well, notice that we've already calculated the probability of C and D. If these two events were mutually exclusive, this probability would be 0. They can't happen at the same time. But we know from part A that the probability of C and D is not 0. It's 0.3, so they're not mutually exclusive. What about independence? Okay, if we condition on D, what's the probability of C? If they were independent, it would just be the probability of C. But we know from the scenario that the probability of C given D is 0.6, and the probability of C is 0.4. So we know that those two are not independent. And if they're not independent, what's the probability of C or D? Okay, they have some overlap, so we can use the so-called addition rule for probability and calculate the probability of C or D as the probability of C plus the probability of D minus the probability of their overlap, which is the probability of C and D. And we have all of these numbers, just plug them in, 0.4 plus 0.5 minus 0.3 to give us 0.6. And finally, the conditional probability of D given C. Straight away, the definition of conditional probability is the ratio of the probability of C and D divided out by the probability of C, which is 0.3 over 0.4 or 0.75. Okay, again, if you did not justify your answer completely by stating a formula, by using correct logic and writing out what your logic is, you did not gain full credit for this problem. Okay. All right, let's go to the last problem here. And here again, we have a deck of cards, and we're going to be drawing 2 cards from this deck without replacement. So without replacement means that given a draw on the first card, it will affect the probabilities of a draw on the second card. Okay. So let's go ahead and sketch out what we've got here. So on the first draw, we may get either green or yellow with probabilities 6/10 and 4/10 respectively. Now, depending on whether we have green or yellow, what's the probability of getting a green or yellow on the second draw? So here I've sketched out the branches of the tree. So if we go up the top branch here, that's 2 green cards, one green card followed by another green card. Or we may have a yellow card on the first draw and either a green or a yellow card on the second draw. And finally, we might draw a green card on the first draw and then follow that up with a yellow card on the second draw. So here are the 4 possible chain or paths in the 2-card experiment here, the 2-draw experiment. So let's calculate this path here, probability of G1, that is a G on the first draw, a green on the first draw, and a green on the second draw. That's just this top path up here, this top branch. And we simply now calculate this joint probability using conditional probabilities here. So it would be the probability of G2 given G1 times the probability of G1. And the conditional probability of G2 given G1 is right here. It's 5/9. Remember, you've already taken out a green card from the deck. So 9 cards remain, of which now 5 are green. So that would be 5/9. And that product is 1/3. What's the probability of at least 1 green in the 2 draws? Well, let's do it this way. Let's define the complementary event. E prime, the complementary event of at least 1 green, would be none of them are green, right? That is, they're both yellow. Both yellow is this bottom branch down here, so we would calculate the product of the probability of y1 times the probability of y2 given y1, which is 4/9. And we would then subtract that product from 1 to get the probability of at least one green. Okay, so let's go through this. We've calculated the probability of 2 yellows as 4/10 times 3/9, and we know the probability of the complementary event is 1 minus the probability of the event. Okay, so we would take the probability of E complement and then subtract it from 1, and that would give us the probability of E, which I've done here, and that turns out to be 13/15. Okay, all right. And then finally, let's calculate again this top branch, the probability of G2 given a green card on the first draw, and that's 5/9 up here, right? Okay, and then the last problem is a calculation to decide whether these two draws, green on the first pick and the green on the second, are they independent? And you can see from the tree diagram that they're not. Okay, some of you did state it that way, and I gave you full credit for that. If you wanted to be more precise, you could simply show that the conditional probability of G2 given G1 is equal to the probability of G2. That would show independence. It's telling us that whether you condition on G1 or not, the probability of G2 given G1 is the probability of G2 by itself. Okay. All right, we've already calculated this conditional probability on the left, and we saw that to be 5/9. So what's the probability of G2? Well, to get a green card on the second draw, you can either pick a yellow or a green card on the first draw, followed by the green card on the second draw. Okay, so let's calculate the probability of those disjoint events. Okay, and the first path here we've calculated to be 6/10 times 5/9. So that's the green card on the first draw, followed by the green card on the second draw, and that's the product 6/10 times 5/9. Okay, and then the other way to get a green card on the second draw is to pick a yellow card first, and then the green card on the second draw, and that probability is 4/10 times 6/9. And if we add those two numbers up, we get 3/5, and it's clear then that the probability G2 given G1, which is 5/9, is not equal to 3/5. So these two are not independent. All right, that concludes our worksheet 3. All right, so let me end it here.